I have to share screen. So I have to share screen, which I think I now know how to do. Let me know if you can see it. Can everybody see my screen?
Yeah.
Excellent. Okay. All right. So so I'm going to talk about skinning maps and the lost theorem of Thurston. And this is joint work with Dick Canary and Ken Bromberg. And I have to confess, it's not, the preprint isn't out yet, but it will be, as soon as we can get our act together. So the plan is I want to, this is kind of an old-fashioned topic, as you might guess from the fact that there's a lost theorem of Thurston in it. So I want to talk a little bit about three manifolds and their hyperbolic structures, explain to you what the skinning map is and how it relates to a gluing problem for finding and controlling hyperbolic structures, and then state this this theorem, which the point of it is that we have a proof of it, and say something about that. Okay, so first of all, what three manifolds are going to be in this talk? So the category is compact, oriented, irreducible, atoroidal, with incompressible boundary, but mostly I want to focus on kind of three different pictures of three manifolds that will illustrate most of what I have to say. So the first one is the very simplest from my point of view, which is just a product of a surface and an interval, which you could sometimes call a product I bundle. And okay, that's a nice three manifold. It has two boundary components. It's going to be important in a minute. A slightly more complicated one is a book of I bundles, in which you just take a bunch of so here's an I bundle, except that it has a boundary. The surface has a boundary, so there's an annulus in the boundary of the I bundle, which is important. You take several of these and glue them together by taking the annuli and mapping them onto the annuli in the boundary of a solid torus. And I color coded it so you can see what I mean. I'll try to mostly stick to these sort of schematic pictures where you see this is the solid torus and these are the I bundles, just because it's easier to think about what's going on. So that's a book of I bundles. And I want to say, actually, in some sense, already in this example, the main things we want to talk about are going to be relevant. So even though it's not a very complicated three manifold, the geometry is interesting. And then the third type is really more of a loose category than a type. It's acylindrical three manifolds. So that just means that there are no essential tori, no essential annuli in a manifold. So an annulus is a map of, well, some kind of immersion of an annulus into the manifold with the boundary going to the boundary. It's essential if it can't be pushed into the boundary. And it's hard to draw such a manifold because you have to draw the fact that there aren't any annuli. But whereas, let me just go back to a second. There are a lot of annuli in this picture. For example, if you take any circle on one of these surfaces and join it to the other side, that's an essential annulus. Moreover, inside the solid torus, there are some essential annuli. But it's maybe worth saying, this is part of the standard kind of characteristic manifold, submanifold theory in three manifolds. Those are really all the annuli in this picture. You can't have annuli whose boundaries sort of go from one side of this to the other. So you can control the annuli in this picture. All right, so acylindrical manifolds are a third category to think about. What about geometric structures? So all of these manifolds I have in mind, they all admit hyperbolic structures. And by that, I mean that the interior of the manifold is a complete hyperbolic manifold. So it's obtained as the quotient of the hyperbolic three space by a discrete group. And specifically, I want to think about convex co-compact structures. And a structure is convex co-compact if in the sphere, so in the hyperbolic space has a sphere at infinity, which is just a two-sphere on which the isometries act conformally. And there's a dynamical decomposition. The two-sphere can be written as the union of a closed set called the limit set and an open set called the domain of discontinuity. And what it means to be the domain of discontinuity is that the group action on omega is nice enough that there's a quotient surface. So if we take H3 union this open set, and take the quotient by the group action, we get a manifold with boundary. And the condition of convex co-compactness is equivalent in our setting, at least, to saying that M is homeomorphic to this manifold with boundary. Okay, so that's a convex co-compact structure. Okay, I wanted to give some pictures of what these things look like. So I don't think I can give a talk without drawing a picture of a quasi-Fuchsian group. So here it is. This is the case of an I bundle. Here in the corner, it looks like the flag of Italy, but it's actually an I bundle with a red and a green boundary component. And so what the group looks like is acting in the hyperbolic space is it has a limit set, which is this Jordan curve that I've tried to indicate like that. It goes around the back. And it splits the sphere into two parts, two disks, the red one and the green one. And the idea is that the group, the quotient of each of these disks by the group is the corresponding boundary component. And what's happening on the inside is there's three-dimensional interior, which is the hyperbolic manifold. So that's kind of a cartoon of a quasi-Fuchsian group. Of course, people have been drawing much better pictures of these. So I felt I should at least indicate to you what an actual limit set of a quasi-Fuchsian group looks like. And this is an example of one. So they're kind of pretty and fun to think about. Okay, that was the case of the I bundle. And already there's a lot to say about the geometry of that picture. Okay, then the book of I bundles. So the one I've chosen here has three boundary components, red, green, and yellow in the corner there. And this is roughly what the limit set will look like. Again, every boundary component lifts to these disks in the sphere. But now there are many disks because the group is more complicated. So for example, so this disk here has the property that it has a stabilizer in the group gamma. And the stabilizer acts just on the disk, and the quotient of that is a copy of this red surface. But the rest of the group translates the red disks to all these other little red disks that I've tried to indicate elsewhere in the picture. And each of them has a stabilizer, it's a conjugate of the original one. And so all of them together, and so any one of them kind of will give you a picture of the universal cover of the red surface in there. And similarly for the green and for the yellow. And okay, so that's one aspect of this picture. There's all these disks floating around. And of course, the complement of the disks is the limit set, which you can sort of see. That's what's in blue over here. And of course, I've only drawn this picture to finite depth because it literally takes forever to draw the whole picture. So that's my attempt. Now, an important thing I want to point out here is that, for example, if you look at the red disk here and the green disk here, their closures are not disjoint. Each of them has a Jordan curve that is its boundary. That you can sort of see it traced out like this. But the two Jordan curves are not disjoint. They meet on sort of a Cantor set. And so there's a kind of a Cantor set sitting here, which is the common boundary of the red and the green. And what is that Cantor set to us? Well, if you look back at the three manifold and remember the full picture I drew before, there are these two subsurfaces, this one and this one, which bound I bundle together. So they're homotopic. This and this are homotopic, which means their fundamental groups are identified in the manifold. So they have a common, so the fundamental group of the red boundary component and the green boundary component intersect in the fundamental group of the I bundle. And that fundamental group, as a subgroup of the big group gamma, has a limit set, which is exactly that Cantor set. And that is kind of a way for the green and the red surfaces to interact geometrically. And that is relevant to our discussion as well. Okay, so you can see that in this example. I don't have a computer picture of one of these. I didn't find one. So this is, you have to live with my picture. And then the third example that I had in mind was the acylindrical manifolds. And in that case, everything I said except to the end is the same. You have a bunch of disks. They're color-coded by the components of the boundary. So now my schematic is almost meaningless. It just says that there's a manifold with two boundary components and no annuli. In this case, so the whole story is roughly the same, except that the closures of the disks are disjoint. And that's because the groups associated with the red and green boundary component have no elements in common. And so what I get here is a kind of collection of disjoint closed disks, and the closure of their boundaries is the limit set, which is kind of all this white space I left in the picture is places where I should have filled in with more little tiny things, and sort of the limit of all that is the limit set.
Wait, Yair, can I ask about your last slide real quick?
The one before this,
Yeah.
yeah.
So how does that schematic on the top right match up with your original picture of a book of I bundles? Like I remember you were gluing surface cross I to the solid torus.
Right.
Where were there two half surfaces like connected by intervals?
Oh, sorry. Let me go back to that picture. Hold on. Whoa, there we go. So what are so this boundary component that I kind of outline over here?
Yeah.
What does that look like from the pieces? It's got this subsurface here, the top of this
Oh,
I bundle and the top of this I bundle, if I chose the right ones, attached together along the boundary of the solid torus to make a boundary component. And similarly, this one and this one make a boundary, and this one and this one make a
Cool.
boundary.
Okay, thank you.
Yeah, I'm glad you asked the question because I went through it sort of fast. Okay, and so you see that this subsurface of this boundary and this subsurface of that boundary are homotopic. Okay, maybe one more thing while we're doing it. There's this element, the core of the torus, which is common to all of the boundaries, and you can see that in the picture I drew up. Hold on, in this picture, that element is going to be common in well, one of the conjugates corresponding to that element is going to be the one that's common to all three of these boundary components. Its fixed points are here and there. Right? There's an element whose axis goes through the middle of the manifold, which belongs to all three boundary components. Okay. Any other questions? I am going kind of fast, I realize. Okay. So yeah, so my goal here is to get kind of a picture of what's going on in everyone's mind, so that then when I say all sorts of wrong things, you can catch me. Okay, so the acylindrical case was a bunch of disjoint closed disks and a bunch of groups, stabilizers that don't have any common elements. Here I do have a picture that was drawn by somebody else. This one I think is due to Kurt McMullen from probably the 90s. You will immediately notice that all of the Jordan curves here are circles, and you might ask, what's that all about? And the answer is that a generic element in this deformation space of groups looks more like this. It doesn't have circular boundaries, but there's a theorem which follows from Thurston's geometrization theorem and the Mostar rigidity theorem that implies that every one of these manifolds has exactly one structure for which you get actual circles in the boundary. So that's an important sort of feature of theory that you can do that. Okay, so those are the pictures. The next kind of old-fashioned theorem from the 60s is the Bayes simultaneous uniformization theorem, which tells us how to put all these different convex co-compact structures together. So we fix a manifold M, and we consider all convex co-compact hyperbolic structures on M, exactly the things I had in the previous slides. And Bayes' theorem, translated to kind of the current language, says that this set of all convex co-compact structures can be identified with the boundary of the with the Teichmüller space of the boundary. So maybe I just kind of assumed everybody knows what a T is. So that means the Teichmüller space of the boundary, which is to say the space of all conformal structures on this surface. I should say this is not just Bayes. There are other names here. Alfors was involved in some of the theory, and Maskett, and Kra, and Marden, and Sullivan. There are there are many variations on these theorems, and the theory was worked out kind of over the course of several papers. Anyway, so there's a correspondence then between convex co-compact hyperbolic three-dimensional structures and conformal structures on a surface. And what is the correspondence? Well, it's exactly what we said before in the definition. If you have a convex co-compact structure, then it's a structure on M, but by definition, by the definition I used for convex co-compact, it means that the boundary of M can be identified with omega mod gamma, and omega mod gamma is a conformal surface because it was obtained from an open set in the Riemann sphere by a group of Mobius transformations. So it has a Riemann surface structure, and so it gives you an element of the Teichmüller space. And I should point out specifically for the product I bundle case, this Teichmüller space of the boundary, well, it's the Teichmüller space of a disjoint union of two surfaces. So it turns out to be the product of two Teichmüller spaces, one component for each, one factor of each component, where the bar here indicates that I'm taking one of the components with the opposite orientation. I was just teaching a course on manifolds this year, and so I spent a lot of time explaining what the boundary orientation is. So I'll assume everyone's been to a lecture like that at some point. Okay, so that's the Bayes simultaneous uniformization theorem. And you might say that we're done because we have just described the space we're interested in, and we have a theorem that says how to parameterize the space. So there's nothing else to ask, right? There's nothing else to know because we have parameterized the space. Okay, so what could I possibly be interested in doing with this? So I first want to sell you on the problem of uniform models. So what do I mean by that? I mean the following fuzzy question we have this parameterization using points in the Teichmüller space, and we understand Teichmüller space really well. There's lots of parameterizations of Teichmüller space, very concrete ones, coordinates. There's lots of things to say about Teichmüller space. We know exactly what it is. So given a description, when I say data, it's kind of a weird word to use. Given a description of a point in the Teichmüller space, how do we answer geometric questions about the corresponding three-dimensional hyperbolic structure? And so geometric questions are, there's an infinite list of them, but you might ask about the volume of various subsets, about diameters. You might ask about the injectivity radius. You might ask about the length spectrum in general, various geometric questions you can ask about the three-manifold. And presumably all of it is encoded in here by the Bayer's theorem, but it's kind of a hard question to really understand that, to be able to give any kind of effective answer. And when you say effective answer, it's obviously up for grabs what that means. So one kind of solution in the case of an I bundle was given by work that I did with Howie Maser and Dick Canary and Jeff Brock. And that was, for historical purposes, that was the work that led to the proof of the ending lamination conjecture. But in particular, it gives you a kind of way to understand the internal geometry of these manifolds as a function of the data in the Teichmüller space. And let me try to, I don't want to really get into the details of it, but I need just to say enough of it so that you understand roughly what I'm talking about. So what is the shape of this kind of solution? Well, it's this. You start with a point in the Teichmüller space, which is to say a pair of points in the two individual Teichmüller spaces, and then you turn them into a combinatorial object. So I guess actually I didn't write that here. Let me sort of say you produce some combinatorial data that describes the points in Teichmüller space. For example, you could choose minimal length Pants decompositions. That's most of the data in the two copies of the surface that are associated to the two Teichmüller points. And then, okay, that's combinatorial data. And then you can connect these two combinatorial objects by what is called a hierarchy path in the curve complex of the surface. And again, I'm going to not talk about that really, but it's some kind of combinatorial structure that you can really think about and get information out of. And you get an explicit path in there. And then that path can be converted into an actual model, which is to say an actual manifold, a three-dimensional manifold with a geometry. And it comes equipped with a K by Lipschitz homeomorphism into the hyperbolic three manifold. So that's what I call a model. And when I say uniform, I said uniform on the other slide, I mean that this, well, at least that this K depends only on the topology of the surface and nothing else. So, so that it's uniform in the deformation space associated to S. Okay, and it's, okay, that's the kind of thing I mean by uniform model. And part of what I want to talk about is the desire to produce such a uniform model in the other cases also for the more general manifolds. And you might say, well, don't we already have that because we understand their boundaries, because their boundaries sort of reduce to thinking about things like this? And the answer is not quite. There's not a complete discussion of how to do this for a general, for one of these general manifolds that's uniform over the whole deformation space. So that's part of the goal. And I'll come back to that in a few slides. So how am I in time, by the way? I guess I'm okay, I think. Okay, so that was one thing. Uniform models is one subject to think about. Now I promised to talk about the skinning map. So let me tell you about the skinning map first, and then about how it relates to the gluing problem. So let's go back to our manifold and fix a boundary component S, and make the following observations. So the fundamental group of S injects into the fundamental group of M. This is part of the, I guess in the very beginning, I said I wanted to think about incompressible boundary manifolds. That's what incompressible means. But certainly in all our examples, that's, in all of the explicit examples, that's true. So because the boundary injects like this, I can take a cover. There's a corresponding cover of this manifold by a manifold that's essentially this one, or I guess the interior of this one. So I can take, so let's be clear. So I take M and I take the cover associated to the boundary component S, and that is a manifold homotopy equivalent to S. And so I get, I go from, that means that if I have a convex co-compact structure on M, I can lift it to a convex co-compact structure on S cross 0, 1. I should say it's not obvious that it's convex co-compact. So there's something to check here, that you really get a convex co-compact structure and not some other different structure. But that's it. The passage that covers gives me a map from this deformation space to this deformation space. Okay. And then what happens on the level of the Bayes parameters? Well, you start with a Teichmüller point in the Teichmüller space of the boundary of M, and then you observe the following thing, that if you look at this structure on S cross 0, 1, it has a Bayes parameter which consists of 2 points, mu, and I'll call them for a moment mu s plus and mu s minus, which live in here. Now, it turns out, you'll see in the next slide why I'm saying this, that mu s plus is just equal to the original Teichmüller parameter at the surface S. But the other one is something new. And it depends on the data that I started with. So mu s minus is a holomorphic, well, the holomorphic part is just for fun. It's for us, I won't be using this fact, but it's part of the general theory that it's a holomorphic function. That's kind of part of the Alfors-Bayes deformation theory. Anyway, forget the holomorphic part. It's a function of nu, that's what we care about. And then in a minute, we want to assemble all of these for all of the boundary components and get a kind of big function of nu, and that would be the skinning map. But first, the picture. So this illustrates the following proposition. If you spend an hour drawing a picture for a talk, then you're gonna want to use the picture twice. So here's a picture of the from before of one of these actions of the group. This one was associated with the acylindrical manifold. And what I'm doing here with this arrow indicates that I'm focusing my attention on the stabilizer of this one red component. So here it is, the red component. And on it, there's the action of its stabilizer, which is the fundamental group of the red boundary surface of, let's call that one S. So S is somehow associated to this thing. And on the other side, I've erased the coloring. So it's like I've forgotten the rest of the group action. So now I only have the stabilizer acting here. So it preserves the red disk and it preserves the complementary disk, which is now a white disk with lots of blue stuff on it. And that's where the data comes from. So the data on this one produces mu plus S. Whoops, I think maybe I forget how I use the superscript here. And on the other side, the entire other side gives rise to mu minus S. And mu plus S, therefore, is just the same as I had before, mu S. But mu minus S is something new that's come out of erasing all the colorings on the other side of the disk. And that's the skinning map, is to do exactly that thing. More specifically, if you combine over all the components of boundary M, then you get a big map that takes a point in the Teichmüller space of the boundary, mu S, and replaces it with all the mu S minuses for all the S's in the boundary. So you'll note that these are the same dimension, Teichmüller space. And that's the map, that's the skinning map. Okay, so first of all, you look at it and you say, that's a cool thing once you think about it, right? That's one motivation. But of course, it arises because of a real application in mind that Thurston had. And so that's what I want to talk about. Let me pause for a second. Are there questions about this? The skinning map always takes a little while to absorb. Okay, I can't see the chat.
Oh, so go ahead.
Go ahead. I said I can't see the chat, so if somebody wants to tell me what's in the chat.
Oh, that was you. Okay. Can you explain the terminology? I mean, obviously the boundary is the skin, I guess, but I
think that's all it was. So I think Thurston's terminology was that you peel the skin off of the manifold. This is the skin, and you peel it off, and you look inside to the other side, and what do you see? That's why he called it the skinning map. I think it's better if you think of it as like skinning an apple than if you think about it. You don't want to think about skinning any mammal for this. That would be uncomfortable. So yeah, that's the reason for the name. Okay, so what do we do with the skinning map? So what we do with the skinning map is we think about the gluing problem. The gluing problem occurs as the inductive step in Thurston's proof of hyperbolization of Haken 3 manifolds. So the proof that they admit under suitable conditions admit hyperbolic structures. And at this point, you could already stop and say, why are we interested in Thurston's proof? After all, we now have Perelman's proof, which proves it in greater generality. So what's the point? Well, and I say, my response is essentially, first of all, every proof teaches you something else. And so every proof should be cherished. That's one thing. But The other thing is that it's possible to get more quantitative understanding from Thurston's proof than just the mere fact of existence of hyperbolic structures. And that's kind of what I'm after, is to have a more kind of overall quantitative understanding of what's going on in this process and how we understand the manifolds that we get. Okay, so what is the gluing problem? So you start with one of our manifolds that we had, and you imagine you have an involution tau, which is a homeomorphism from the boundary to itself. It's an involution, so it goes both ways. It's orientation reversing, and it's fixed point free. And that means that that when you glue the manifold together by identifying along tau, you get a new 3 manifold, which is still oriented. And that's what this picture indicates, that I take the 2 boundary components in this case and glue them together. I should say it's possible for the manifold to be disconnected and you're gluing together 2 different ones. And it's also possible for there to be just one boundary component that you're cleverly gluing to itself. All of these things are possible, but we're just going to stick to this picture. Okay, so that's, and what you want to do, what Thurston wants to do in his proof is to show that if you know what happens here, if you have hyperbolic structures here, then you can arrange for this one to have a hyperbolic structure. It's a gluing operation. So here's the theorem. The theorem is, if M admits convex co-compact hyperbolic structures, and then M mod tau has no topological obstructions. And topological obstructions are essential tori. Let me draw them in a second. So in that case, M admits, if that's true, then M admits a hyperbolic structure. That's the theorem. Let me point out, what do I mean by these essential tori? So let me say, a hyperbolic manifold can never have an essential torus, because an essential torus would correspond to a 2-generator abelian subgroup of PSL2C that isn't parabolic, and there are no such groups. Or if you like differential geometry, if you had an essential torus, you could find a minimal representative and it would be negatively curved, but tori can't be negatively curved by the Gauss-Bonnet theorem. So anyway, so there are no tori, so there can't be tori in this picture. How could a torus have suddenly appeared in M mod tau? And the answer is, well, let's see, there could, if it was like this and if it was an essential torus that didn't touch the gluing boundary, then it would have already been there in M. And that couldn't be true because M was already non-toroidal. So that's not what happens. What has to happen is essentially this. There's a curve in the surface that can be joined through the interior of the manifold and back to itself, or maybe in several steps back, maybe as several curves. And that picture I've drawn is a torus. And if I've chosen the green curve to be essential, and if I had this annulus available inside M, then it could give rise to a torus, right? So tau might allow such tori to arise by cleverly matching up the boundaries of annuli. And if that doesn't happen, Thurston proves that there is a hyperbolic structure. So that's the theorem. What does it have to do with a skinning map? So let's relate the process of gluing to a fixed point problem that's associated to the skinning map. So here's the same picture again. Here's our glued up manifold. And now instead of thinking about just cutting along the surface, I want to think about taking covers. So because M is the subset of M mod tau, I can take the cover associated to M. And what do I get? I get this manifold with whose core looks like the original M, but then it's attached to it are these infinite regions which cover, which somehow map downstairs and cover. If there's a hyperbolic structure on this manifold, then it lifts to a hyperbolic structure here. And I've color coded the sides of the boundaries here. So in this boundary component, it's got an outside half, which I've color coded red, which corresponds, if you follow my little diagram, to this side of it on the after gluing. And then the other boundary component has a green part, which glues over in the green direction over here. It covers, its covering map in here starts off matching the green side, and then it kind of runs all over the place. So there's a big covering map here. And then there are further covering maps for each boundary component. There's a surface group. This guy is an I bundle, which is associated to this boundary component. And this guy is an I bundle associated to that boundary component. So these are the product manifolds that we first drew in the beginning of the talk. And they are actually the same. These are the same. Why are they the same? Because both of them cover the same surface down here. So they are geometrically the same manifold, but the map that indicates that they are the same is tau. right? Tau is the map that shows that these two manifolds, that's an isometry between these two manifolds. On the other hand, if you look a little further, what else do you see here? You see that when you took this covering map, the red end lifted to the red end here, and so whatever you see on the inside is the skinning image of this associated to this boundary component. And similarly, for this boundary component, what you see on this side is the skinning image for that boundary. So if you put this all together and kind of don't blink too much, you will see that what I'm saying is this. I'm saying that if I have a solution, then it corresponds to a fixed point in the Teichner space of this map. I had to find data so that the boundary of M has in this case 2 copies of the surface in it. So it's 2 Teichner spaces. I have to find a structure here and a structure here, which have the property that if I apply the skinning image, the skinning map to go from the outside to the inside, and then apply tau to match them up with the correct gluing, then they have to agree. They have to, each one gives the other one, and which is the same as saying that the pair goes back to itself after applying exactly sigma followed by tau.
And when you say solution, you're trying to find a hyperbolic structure on M given one on M mod tau. Is that right?
No, the other way. Good point. Yeah. So a solution means that I want to. Sorry. Yeah. What do I mean? Solution is I want to find a hyperbolic structure here. How am I doing it? I'm looking for a structure here, which will carefully match itself on the boundary so that it gives me the structure on the glued up manifold. So what this diagram shows directly is that if you have a solution, then it corresponds to a fixed point. Then you kind of trace through this diagram and you see that what I've really produced here is a fixed point of this combined map, okay? And what Thurston also proved using the Klein-Masked combination theorem is that the converse also works. If you have a fixed point, then it gives rise to a solution, to a metric on this manifold. And so therefore, he's reduced the gluing problem to a fixed point problem. And that's kind of where this kind of the starting point of what I'm really interested in, which is I want to understand. I want to understand in a more precise way what is the geometry of this fixed point going to look like? Where is the fixed point going to be, and so on. So here now we're coming up to the theorem. So Thurston proved that a fixed point exists, and he did it by using many of the same ideas that feed into everything we're talking about here. But while he gave this proof, he also made a stronger statement, which is the following. The statement is that given M, there's an integer k, so that provided that we're in the setting where we will find a solution, providing we obey the topological restriction, power of this map has bounded image in the Teichner space. So kind of maybe you should have so Teichner space is an infinite diameter metric space, and we have a map that this combined map takes the Teichner space to itself. And if the image was to live in a pre-compact set, in a bounded set, then it's much easier to show that there's a fixed point. And in fact, Thurston showed that there's a unique fixed point and so on. But getting this boundedness is important. And so and Thurston stated that while the map may not have bounded image, some known power of it does. Some a priori known power of the map has bounded image. Now so what's the history of this? So Thurston gave the statement, but nobody actually knows the proof. So we've kind of talked to all the people who were there at the time, and nobody can remember a proof. All the proofs that were written down of the geometrization theorem, they show that a fixed point exists, but they do not show this stronger statement. So that's what I mean by a lost theorem of Thurston. I actually have no idea what his proof would have been. Okay, so I'm interested in this theorem, so I want to prove it. That's what we're talking about. Now I should say, when M is acylindrical, that our third category, then this whole thing becomes more manageable. And here's what's true. What's true is in that case, first of all, the topology is easier. M mod tau is always atoroidal because it's exactly the picture I drew before. If M is acylindrical, there are no annuli to work with and no way, nothing to match up to get a torus. So the quotient is always atoroidal, and therefore there should always be a fixed point. And what Thurston proved in that case is that already after applying the skinning map itself, without tau being involved, the skinning map is already has bounded image. This is what's usually called Thurston's bounded image theorem. And he gave more of a sketch of this proof, but a full proof was only written down by Autumn Kent in 2010. And even in that case, it's a little that uses sort of more machinery than was around when Thurston gave his original discussion. So even in that case, there's something to say. Okay, so we want to understand. We want to talk about this theorem in the generality I've said. Okay, so right. So I wanted to use another picture twice. So if I do the same thing in the cylindrical case, I want to kind of illustrate how it is that the diameter of the skinning map itself is infinity in this case. I'm not really going to prove that either, but I just want to kind of point out where's the issue. So remember, we get to vary the conformal structures on all of the boundaries. So the red, green, and yellow surfaces are all kind of moving around kind of unboundedly. And then we produce the skinning image, which reads off the other sides of everybody. So for the red component, this thing is the other side. And I want to point out that the structure of this other side is heavily influenced by the parts of the green and yellow surface that are in common with the red. So for example, if you take an element, there's an element of the common subgroup, say maybe its axis goes like this. It's got endpoints in a Cantor set. So that, the geometry of that element of the group is heavily influenced by the green surface. And it's not maybe hard to imagine that by deforming the green surface very, very much, you can change the geometry of that curve in the white surface here, because it has such a big piece of green really right there kind of attached to it. So that is the reason, in a kind of very vague way, why the diameter is infinity in the cylindrical case. It's because the two surfaces communicate, the two sides communicate, and that affects the skinning map. Okay, so we have to somehow get control over this enough to explain why the iteration eventually has bounded image. So I want to say a bunch of things about the proof, but they're mostly going to be hand waving, and I guess that this whole talk has been hand waving, so maybe that's of a piece with it. So a little bit of kind of color-coded notation. The first part I want to talk about is where most of the geometric work is done. It involves building a model for the manifold, and I want to lean on the fact that I claimed that I know how to build models for I bundles. Okay, so what do? I start with my manifold. Let's stick to the Book of I bundles picture. And so here's the solid torus, and here are the I bundles. And I label the boundary components with these colors, as you see. And then also on the solid torus, there are three special curves, which are curves in the boundary, which are also in the boundary of the solid torus. So there are three separate curves on the boundary in this case. Each one of them lives on the corresponding boundary component. And the first step is to observe that, it's not an observation, it's a claim, sorry, that there's some kind of combinatorial projection of this data on the boundary to give us data on the complement of the curves gamma in S. So in particular, what am I saying? I'm saying that, well, first of all, I'm going to give you a magic word. The magic word is subsurface projections. I'm going to try to get through without defining them. But the point is, you take combinatorial data on the whole surface, you intersect it with a subsurface, and you read off some combinatorial data on the subsurface. And that's a kind of very, very kind of synthetic combinatorial thing to do, which is not obviously related to geometry, to the geometry of the manifold. But it gives you a bunch of data. So for example, in this little diagram, mu1 will project to give you a kind of a marking mu1 that lives in the complement of gamma1. So let's write it here. Mu1 lives in the complement of gamma1, mu2 here, and so on. So you imagine like a curve system living on the surface, on those subsurfaces. And then we use this information to build a bunch of I bundle models from the kind of slide I talked about before. So here's a very rough indication of what you do. You take this picture, and you take all the data in this picture and use it wherever possible to build an I bundle. So for example, for each boundary component here, I draw nu1, the nu1 data on one side, and I draw gamma1 and the induced curve system on the other side, and I build whatever the model looks like here. It might be very large and complicated. I do the same thing for each boundary component. And then between the boundary components, for the little eye bundles that I glue together, what I call maybe the internal eye bundles, I take the data that came from the two boundary components, and I use that data to build an eye bundle here. And I do that for each of the eye bundles. Then I glue them all together. And this intermediate region here, what is that? After I glue them all together, this thing I just outlined in red is a solid torus. Because here, every one of these little arcs is an annulus. It's sitting on the kind of the boundary of an eye bundle. And the annuli fit together to make a torus. And I'm claiming that because this thing is supposed to be our original 3 manifold, there's just exactly one way to fill in topologically a solid torus. And there's also a way to give that solid torus a geometric structure. So this solid torus becomes what's called a Margulis tube. So that's kind of the picture, and that's the model. Well, okay, that's and I've left everything kind of unsaid, but there's some process like this which I claim produces a model. And the theorem about this model that we can currently establish is this: it admits a K-Lipschitz proper homotopy equivalence to the hyperbolic 3 manifold, which respects the thick-thin decomposition, and the K, in the kind of the same kind of uniformity as before, depends only on the topology of the manifold and not on the geometry or the combinatorics of the data. So this is kind of a cartoon of that. I've built, here are the eye bundles. Here's one, here's one, here's one, so on. Here's the big solid torus in the middle. I have to add in actually things that go to infinity here, which are not hard to explain, to do. The ends of the manifold are not hard to throw in. And then the little yellow rectangles are meant to be Margulis tubes that the model predicts. Whereas this is the actual hyperbolic manifold with its collection of Margulis tubes. And I'm claiming that these two patterns actually correspond. So this picture predicts the correct configuration of the thick-thin decomposition of that manifold, just to have something to hold on to. And what am I being cagey about? It's right here. I said Lipschitz. I didn't say bi-Lipschitz. It's not a bi-Lipschitz homeomorphism. Now I think that there is a bi-Lipschitz homeomorphism, and I also think that less lazy authors might have written it down, but we have not written it down. So for the moment we have this, but that's enough for our purposes. Okay, so that's what we have. We have this some kind of model for the manifold. And what can we do with the model? Am I running out of time? How much time do I have?
About 8-ish minutes.
Okay, fine. I think I can without overstaying my welcome. I can do that. I think. All right. So the second step is that with this model we can estimate the skinning image, the skinning map, and now I just want to give you again a kind of pictorial explanation. So remember that the idea of the skinning map is to pick a boundary component, take a cover, and then look on the other side from that boundary component and see what you see at infinity. So this is what that corresponds to in the model. Here's the model from before. And then if I take the cover associated to the red boundary component, what do I see? Well, I see the red boundary component. I see this kind of product region above it. They just lift to the same thing. This eye bundle lifts exactly to an eye bundle here. These little eye bundles, they still lift just nicely to here. And the solid torus lifts. But everything that lives out here, there's something to prove here, what I'm claiming. Everything that's out here completely unwinds when you see it here. It kind of infinite to one kind of covering. So back here, you suddenly see some more complicated stuff. And then at infinity, you're going to see, presumably, the skinning image. That's what the skinning image is supposed to capture, is the geometry at infinity of this thing. And I'm claiming that this little purple layer here, the lower boundary of the part that lifted, is a really good estimate for the skinning image. Even though it lives inside the manifold and not at infinity, we can get estimates on the skinning image from this information. Okay. All right, all of this is without any details. So what I want to now say a little bit more about is the kind of topological endgame of the process. Since this is the topology conference, I feel like this is the place to do something. So I want to explain how control of the skinning image propagates in some finite way until you control everything. And let me first give a kind of fun topological definition. If I have two subsurfaces on the boundary of the manifold, then I say that Y escapes from Z if the following is true. If I can build a cylinder based on Y so that the 0 level of the cylinder is the identity and the 1 level is disjoint from Z. That's the escaping part. And it's not a trivial, it's a real cylinder. It's not homotopic into the boundaries, a map of pairs. Then Y escapes from Z. So here's a picture. The picture here, Z is this purple surface here somewhere in the manifold. Y is this green annulus. And there's an essential cylinder here which takes Y to be disjoint from Z. And so Y has managed to escape. Okay. Note that it does not help Y to be itself disjoint from Z, because you can't escape using a trivial cylinder. You really have to use a real cylinder to escape. Okay, so it's a high stakes escape. And it also wouldn't matter if Z actually was here. If there was some Z that intersected Y, that's fine too, as long as Y can escape by this non-trivial annulus. So that's what it means to escape. Okay, and once you have that, we can define something I'll call omega of Z, the maximal essential subsurface that escapes from Z. And psi of Z is just its complement. And I think of psi of Z is the subsurface that Z controls, and you'll see why I say that. And let's do a couple of examples. So when Z is the empty set, and I'm going to stick to our book of I bundles, if Z is the empty set, it still means something to escape from Z. Even though everything is disjoint from Z, to escape from Z, you have to have a cylinder. So the only things that can escape are the things that live in the cylindrical parts. So all of the red surfaces here escape from Z, because for anything in the red surface, you can build an annulus to the other side, which is disjoint from Z. Now the annuli, these yellow annuli also escape from Z, but they're part of the red, really. They can be, every annulus here actually is homotopic into the red surface. So I'm not going to take them separately. I don't need them. On the other hand, anything that crosses the yellow cannot escape from Z, because it has no cylinders at all. And so that means that omega is exactly the boundaries of the I bundles. And they leave, and then psi over here is exactly the yellow annuli, because it's the complement of the red surface. Okay, so the main property of psi that's important is that nothing that crosses psi can escape from Z. That's the property of psi. Here's a more complicated one, just to have something. If Z is the purple, the union of these two purple boundary components, then the only way to escape from Z is to be in this red surface or this red surface, which have annuli that escape out here into the open air. But neither of these can escape from Z, because their annuli just take them. You start here, you think you see Z right there breathing down your neck, and you escape to the other side, and Z is waiting for you, so you can't escape. So now the omega of Z is these two disjoint red I bundle boundaries. So psi of Z, the controlled part, is this full boundary on this side, and these two pieces over here. Okay. All right. Now I'm really almost overstaying my welcome. I want to make one more remark about this. Psi is monotonic. That's not hard to see from the definition. If you enlarge your surface, then you enlarge the stuff that it controls. This is well known to anyone who plays hide and go seek or whatever games correspond to this. Okay, so now what? Now I want to give you one more geometric thing, and maybe that'll be the end. So first of all, here's a little one more geometric remark. If I have a subsurface of a bigger surface, then there is a restriction map of the Teichner space. If I have the Teichner space on the big surface, by restriction to the subsurface gives me an element of the Teichner space of the smaller surface. I'm reminded here I'm supposed to give you fine print. The fine print here says that the Teichner space of the empty set is a single point. I need that just for the definition to work out correctly. And also by Teichner space, you have to be a little bit careful. It's a Teichner space of surfaces that are allowed to have boundary components. So it's a slightly more general Teichner space. So anyway, but let me, that's a fine print. So the geometry that I didn't really explain in parts 1 and 2, the whole thing with the models and estimating the skinning image, gives us the following theorem. Okay, this theorem, what does it say? It says, if you start with a surface in the boundary and a compact set in its Teichner space, then there exists a compact set in the Teichner space of its controlled subsurface, so that there's control. So that if you start out in RZ inverse of K, that means if you start out in the Teichner space of the boundary, but only those things which when restricted to Z, are bounded by K, if you take those things and take their skinning image, you land in the set where psi of Z is controlled by L. So in other words, if you have control on Z, the Teichmüller data has control on Z, it propagates to control on psi of Z after you apply the skinning map. Okay? That's what the theorem says. And I claim that that's what you need. How many seconds do I now have, Dan?
Just you can wrap up with however much.
Okay, I think I have just one slide, so I will. The rest of it is something that not so hard to kind of to imagine you can do, which is the following: you make a sequence of nested surfaces. You start with the empty surface, and then you apply psi followed by tau to each one, and the theorem says that you can control the skinning map successively on each one of them. You start out, you obviously control the empty set, and then you start controlling everything else. And it turns out that what exactly you get is that when you iterate our map I times, you end up in the subset of the Teichmüller space where Zi is controlled by Li. And so you have a sequence of growing surfaces, and at some point they either have to stop. They can't change forever because of topological complexity. So at some point they stabilize. And when that happens, one of two things happens. Either that surface is the whole boundary, in which case you have completely controlled the Teichmüller data, and you're done. Or, I lied, I have one more slide, sorry. Or it isn't the whole boundary. And then this kind of short answer is that that the boundary of what you get, this thing, if it's not everything, then it has a bunch of boundary curves. And now I claim the way I've set things up, the boundary curves will bound a union of annuli in M, which assemble to essential tori and contradict our topological hypothesis. And I think I am out of time. So let me leave you with what the picture, well, maybe this was supposed to be an illustration of why you get these tori at the end. And maybe I'll just leave that unsaid and say thank you.
Great. Let's thank Yair. Thank you for the picture of Buzz. That's our mascot for those of you who don't know. We'll open it up for questions from the audience.